With the complicated geometry of the ventricles, you can imagine that at each point in time, there are vectors of different amplitudes showing into different directions in the heart. From all these momentary vectors, an average vector can be constructed for each point in time. The sequence of these average vectors over the time of ventricular depolarization enables us to construct the vector loop, which you can see here. The vector loop is the line that connects the tip of the arrows here. The strongest or longest of these average vectors, shown in red here, is called the main vector. And where this vector is showing determines the electrical axes of the heart in the frontal plane. The most exact way would be to exactly determine and calculate the direction of the main vector in the frontal plane. For example, we could calculate if the main cardiac vector is showing into the direction of minus 60 degrees, minus 90 degrees, or plus 120 degrees on the Cabrera circle. However, this is way too time-consuming and really not worth the effort because there are only a few situations where knowledge of the axes really makes a difference, and we'll get to those a little later. But in almost all countries, it is the rule to include information about the electrical axes in a complete ECG report. So we should be able to find the most important abnormalities of the electrical axes, and here is a simple trick how you can do it. We should remember that if the cardiac axis is showing into the direction of a certain lead, as lead 1 here in this example, then the deflection in that lead will be mainly positive. When the vector points away from that lead, we will get a negative deflection in that lead. Of course, the same also works for lead 2. So if the main vector points into the direction of lead 2, then lead 2 will be mainly positive. Taking these two informations together, we can see what happens when lead 1 and lead 2 have predominantly positive deflections. Let's check it out. So we said lead 1 is mainly positive. The cardiac axis is showing somewhere in the direction of the yellow area. Now we take lead 2, and if lead 2 is also mainly positive, we know that the cardiac axis has to show somewhere at the intersection of the yellow and blue areas. And the mixture of yellow and blue is green, as we know. So the cardiac axis has to show somewhere in the direction of the green area, which is minus 30 degrees to plus 90 degrees. And since most vectors in humans show into that direction, this is called a normal axis. The terminology and nomenclature, however, varies in different medical schools and countries, but we will use the terms mostly used in English and American textbooks. So let's move on. When we have lead 1 positive, meaning that the cardiac axis shows into the direction of lead 1, and lead 2 mainly negative, meaning that the main cardiac axis shows away from lead 2, we know that the cardiac axis actually has to show at the intersection of these two areas, at the dark yellow area here, from minus 30 to minus 90 degrees, and this area is called left axis deviation. When lead 1 is negative, we know that the main vector will be found in the gray area. To be more precise, we have to look at AVF now. So when lead 1 is negative, look at AVF. And when lead 1 is positive, we look at lead 2, as we've just seen. So when lead 1 is negative, we look at AVF, and if AVF is mainly positive, we know that the main cardiac vector has to show somewhere into the direction of this dark blue or dark gray area down here. And this is called right axis deviation. That's when the vector points into the direction of plus 90 to 180 degrees. And lastly, if lead 1 is negative and lead AVF is also mainly negative, we know that the main cardiac axis has to show into this area up here. And this area is actually called a northwest axis. It's actually quite rare to find an axis that points into the direction of the northwest axis, and you shouldn't bother about it too much for now. So let's recap. If the main cardiac vector points into the direction of the green area from -30 to +90 degrees, that's called a normal axis. If the cardiac vector points into the direction of the yellow area from -30 to -90 degrees, that's called left axis deviation. And if the cardiac vector points into the direction of the blue area from +90 to 180 degrees, that's called a right axis deviation. And lastly, if the main cardiac axis points into the direction of +180 or ±180 to -90, then that's called a northwest axis. You should only care about right axis deviation and left axis deviation for now. Why? Well, actually, if you have a normal axis, then that doesn't help you that much in your diagnoses. A northwest axis is very rare, but if you have a left axis deviation or a right axis deviation, that can really give you important clues as to the underlying diagnoses. Now let me show you a simple trick to determine the cardiac axis really fast in most patients. Here's how it goes. The first thing to do is to hold the ECG printout as shown here. Make sure that lead 1 is close to your left thumb. If lead 1 is positive, then look at lead 2, which should be next to your right thumb. If both leads are mainly positive, as in this example, and as we've already learned, then the patient has a normal axis. If lead 1, the lead to your left, is mainly positive, and lead 2, the lead to your right, is mainly negative, then you're dealing with left axis deviation. If lead 1 is mainly negative, you should look at lead AVF instead of lead 2. Make sure that the left thumb is next to lead 1 and that your right thumb is next to lead AVF in this case. Then we'll carry on just as before. If the lead next to your left thumb, that is lead 1, is mainly negative, and the lead next to your right thumb, that is lead AVF, is mainly positive, then you're dealing with right axis deviation. And if both leads 1 and AVF are negative, then you're dealing with one of the rare cases of a northwest axis. Some people also call this an extreme axis. So here are the different instances again. On the top half, lead 1 is mainly positive, so we have to look at lead 2 in addition to lead 1. If both leads 1 and 2 are mainly positive, then the patient has a normal axis. If the left lead, that is lead 1, is mainly positive, and the right lead, that's lead 2, is mainly negative, the patient has left axis deviation. In the examples on the bottom, lead 1 is mainly negative, so we have to look at lead AVF in addition to lead 1. If the lead to your right, that's lead AVF, is mainly positive, and the lead to your left, that's lead 1, is mainly negative, the patient has right axis deviation. And if both leads are mainly negative, the patient has a northwest axis. One more thing, sometimes you don't have access to lead AVF, in which case you can use lead 2 instead of lead AVF. So instead of switching to AVF when lead 1 is negative, you stick with lead 2. That's not as ideal, but you'll still get fairly accurate results. As I've said, there are not a lot of clinical situations where knowledge of the cardiac axis really helps you come up with a better diagnosis. But now let's turn to the clinical situations where knowledge of the cardiac axis really makes a difference. Situation number 1. This is the cardiac conduction system. That's the AV node. That's the bundle of His. That's the left bundle branch, which is subdivided into the left anterior fascicle, and the left posterior fascicle, And then there's the right bundle branch. Electrical depolarization that comes from the atria has to travel through the AV node and the bundle of His to the bundle branches to the Purkinje fibers. Now in any of these structures there can be so-called blocks. That is when the depolarization cannot travel through the structure. You can have an AV nodal block, you can have a block in the bundle branches, you can have a block in the left interior fascicle, left posterior fascicle, and also in the right bundle branch, of course. And then you can also have a combination of all those blocks. And when you have a block of the right bundle branch and an additional block in one of the fascicles, we have what is called a bifascicular block. And whenever that happens, you get a deviation of the cardiac axis. So let's assume you have a right bundle branch block. You see this M form over the right ventricle in V1 and V2. And as we've learned, that's a sign of right bundle branch block. If in addition to that, you also have a left axis deviation, then that means that you not only have a block of the right bundle branch, but also of the left anterior fascicle. And this entity is easy to remember because there's a mnemonic that's called left. Left meaning when you have a block of the left anterior fascicle, you have a deviation of the cardiac axis to the left. So left axis deviation is equal to left anterior hemiblock. Now let's turn to another scenario. Let's say you have right bundle branch block plus a right axis deviation. What does that mean? That means that you have a block in the right bundle branch plus a block in the left posterior fascicle. So the take-home message here is, if you have right bundle branch block, always look for axis deviation. If you have left axis deviation, that means that the left anterior fascicle is also blocked. If you have right axis deviation, that means that the left posterior fascicle is also blocked. So that's the first situation in which knowledge of the cardiac axes helps you come up with a more refined and better diagnoses. Now let's turn to the second situation. Whenever you suspect right ventricular strain or right ventricular hypertrophy, it helps to look for the presence of right axis deviation. So for example, let's assume you have a patient who comes into the emergency room with symptoms that are compatible with a right heart problem, with dyspnea and subtle signs of cyanoses. You write an ECG and see signs of right ventricular hypertrophy with the tall R wave in V1 and a deep S wave in V5. And the R to S ratio is above 1. Now this constellation of signs already suggests a high likelihood that something's wrong. Remember our RSS criteria. But when there's also right axis deviation, you almost have certainty that something's wrong here and that the right heart has a problem. So whenever you have a suspicion of a right heart problem, of right ventricular hypertrophy for example, with a V1 and V5 that look like this, plus a right axis deviation, then you have almost certainty that right ventricular hypertrophy is present. In other words, signs of right ventricular hypertrophy plus right axis deviation increases the likelihood of right ventricular hypertrophy. Let's turn to situation number 3. Let's assume you have a patient who has this ECG. V1, V2, V5, V6. What's the problem here? Right, this ECG suggests left ventricular hypertrophy. The Sokolov index is positive. The R in V5 is 2.2 millivolt. The S in V2 is 3.1 millivolt. 3.1 plus 2.2 equals 5.3, and 5.3 is way over our threshold of 3.5 millivolt. So we have a strong suspicion of left ventricular hypertrophy. Now let's assume that this patient also has right axis deviation. What does that mean? Well, it means or suggests that we have biventricular hypertrophy, that both the left and the right ventricle are hypertrophic. These were the situations where knowledge of the electrical axes will provide you with valuable information. What do I mean when I say valuable information? Well, I'm talking about information that will actually help you to refine your clinical diagnoses and make it better. So we can now include this new information into our cookbook. Let's see what has changed. So here's what has changed in the cookbook. We now can add item number 5 to our cookbook approach, and that's the assessment of QRS axes. You should use the step that you have now learned in order to assess the cardiac axes, using lead 1, 2, and AVF. And for now, you should just look for the presence of left axis deviation or right axis deviation. The other two situations, a normal axis and a northwest axis, will not add a lot of additional information to your clinical judgment.
So what's up next? Well, I'd like you to watch the second video in this chapter on atrial enlargement and low voltage, and after that there are some juicy cases and exercises waiting for you. So take care, and I'll see you later.